I want to start chapter 13. In chapter 13, we're going to be talking about statistical tests. So how to, check if two things are similar or check two things are related, or if two things are different, that kind of idea. Most of this stuff that we're going to do in here is going to be, you're going to be using your calculator to do. You're not going to do these calculations by hand. So I would recommend having your calculator out that you can kind of follow along with as we walk through some of these menus and talk about how to do these processes with our calculator, and then how to interpret the results, what is it actually saying. As that's typically the difficult part for students is okay, I did the calculation on the calculator. That's easy enough. It's just a process that I just have to kind of memorize. But what does this number that I'm getting now say about a certain situation? So that's kind of what we'll be talking about here today. So let's start by just kind of talking about a scenario. So imagine you're trying to figure out how long on average it takes to install a new graphics card in a system. The old graphic card installation took, on average, X bar, 2 minutes and had a standard deviation of 0.2 minutes. With the new graphic card, you believe the mean time is 2.2 minutes to install. When testing your new installation times, you want to know if there's a reasonable chance of getting a sample error with an average of 2.2 minutes. This would be considered a sampling error. This means that even if the sample were picked correctly, there's still a chance your randomly picked sample is bad or unrepresentative. So maybe just the sample of new graphic card installations you took just were, by random dumb luck, slower than maybe they should have been on average. Maybe you just got an unlucky sample that somehow is just really unrepresentative of the whole. So you could look back over your old installation times and determine the likelihood or the probability of getting a mean of greater than 2.2 minutes, given that the old card had a mean of 2 minutes for installation and a standard deviation of 0.2 minutes. So what would that look like? So here's our distribution curve of installation times. Since this is symmetric distribution, the mean would be right here at the center. And then let's say one standard deviation is here at 2.2. So the probability of getting a sample of 2.2 or higher is this area underneath the curve. And that area under the curve is this number here, 7.6 times 10 to the negative 24. So the probability of getting a sample from the old installations with that mean would have been this number times 100 to turn it into a percent. So ostensibly 0, right? That's a tiny, tiny, tiny percent chance of okay, I randomly selected some installation times that gave me this mean. Is it still the same? The likelihood is almost certainly not, right? That this is just a slower installation for the new card than the old card. Everybody's okay with that? Okay. That's what we just said. So in this chapter, we're going to look at variables and to determine how they are related to one another. So to start, we need two hypotheses. The first one is called the null hypothesis, or null hypothesis, excuse me. That's what we'll be attempting to prove statistically. The null hypothesis is always assuming, or we do our analysis assuming that the null hypothesis is true, and our analysis is then either going to accept or reject this hypothesis. So in the previous example, our null hypothesis would be that this new graphic card installation still has a mean time of 2 minutes. The alternative hypothesis is the opposite of what you're trying to prove. So it's the opposite of the null hypothesis. It is stated simply to show that what will be true if you reject the null hypothesis. Now, you can't prove a negative, so the alternative hypothesis just allows the data to prove something, or allows the data to directly prove something. I don't know what that's supposed to mean. Your data or experiment may or may not reject this hypothesis. So in the last example, our alternative would be, okay, that the mean time for that new graphic card installation is really greater than 2 minutes. Everybody's okay with that? All right. Note this is not the exact opposite of the null hypothesis. What would the exact opposite be? Yeah, the mean time is not 2 minutes. Because this is only half of that, right? The other half would be less than 2 minutes. But from our data, that certainly seems unlikely, right? Given that the new mean we found was 2.2. All right. So one way that we can test this kind of thing is using something called a t-test, or it's sometimes in other areas referred to as a hypothesis test. And we use that to determine the likelihood of outcomes based on given known data. So let's do a new example here. So this came from your textbook. It says a factory produces light bulbs that are known to last 8,000 hours on average. A new type of light bulb has been developed by engineers and is claimed to last more than 8,000 hours. The management is concerned that the cost of the process producing the new type is more expensive than the traditional method. They can justify switching to the new process only if they have evidence that the new light bulbs do have a longer life than 8,000 hours. To test this, a random sample of 25 new light bulbs was tested, and it gave an average life of 8,600 hours with a standard deviation of 1,000 hours. Okay, so what we want to do is we want to test to see if this new light bulb that we've built really does last longer than the traditional light bulb that we've been used to building, right? Now we've taken it, and the mean appears that it certainly lasts longer, but that's not definitive, right? All that's saying is that the sample lasted longer. It doesn't say anything about the whole. So is this evidence enough to justify shifting to the new process? So let's set up what we know. We know the mean of the original light bulbs is 8,000 hours. That's the mean for our null hypothesis. That's why I put the 0 subscript there. We know the mean of the sample set is 8,600. And we know the standard deviation of the sample set was 1,000. So what we need to do now is set up our hypotheses to test. So our null hypothesis, the thing we want to assume to be true, is that the mean of the light bulbs, the new light bulb design is still 8,000 hours, that nothing has changed. The new light bulb is essentially the same as the old light bulb. The alternative would be the opposite, in which case you'd say that the light bulbs are different, right? That the mean should be more than 8,000 hours, which is kind of what we think is true based on our sample mean already, right? Okay. So let's do this calculation. The calculation we're going to do is called a one-sample t-test. You're not going to know or need to know how to perform one of these on the IB exam by hand. You won't have to do the calculation by hand. But you will be expected to be able to use the calculator to get the number and then interpret the result. But we're not going to talk about how to do this calculation by hand, just like how to get the calculator to give you the number and then what to do with the number afterwards. All right. So we're going to go to our calculator. We're going to press the Edit button. We're going to tab over to the Tests tab. If you have your calculator with you, I invite you to take it out right now and follow along. So again, we press the Stat button. We moved over from the Edit tab to the Tests tab. And we're going to select the first option for t-test. That's option 2. How are we doing, everybody there? Okay. So your screen should look now like this. For our null hypothesis, we're going to enter 8,000. Our sample mean is 8,600. Our sample standard deviation is 1,000. Said we took 25 samples in the problem. And our alternative is that this mean is greater than the 8,000 hours. So we're going to change our option to the greater than. If you have the old calculator, you may not have the color option there. And it doesn't matter what color you pick. After this, you can go ahead and hit calculate. And your calculator should output this information for you. Everybody okay? And if you had the draw option, it would have drawn you this picture. Notice the little darker blue over here? That's the part that it drew in blue. I think it's technically shaded under the curve there. It's just not very much curve height to shade under. Everybody's okay? All right, let's talk about what these numbers mean to us now. So the two numbers we have to interpret are this t equals 3 and this p that's about 0.00310. Why did I round p to that spot? Three sig figs. If I'm doing rounding in this class, how far should I round to? Unless told otherwise, right? Okay. So what do these two numbers mean? Let's start with the t. So the value t equals 3 is referred to as a critical number, and it tells us how far away from the mean our distribution is from the original. on the graph above, the original mean is 8,000. The mean for our sample is 8,600, which is like 3 steps away from the mean. So if I look at these tick marks on the x-axis, that's like 8,200, 8,400, 8,600 is like 3 steps away from the mean. Everybody's okay with that? Now, this number is important but hard to interpret by itself. And so generally we don't do anything with this. The p-value is much more instructive to us. So what the p-value does is it represents a probability. So it means that basically in this case there's a probability of 0.00310 or 0.310% that from a population of light bulbs that have a mean of 8,000, that we could pick a sample of 25 of these that would have a mean of 8,600. So the odds of being really unlucky and picking from a sample of light bulbs that have a mean lifespan of 8,000 and getting 25 of them whose mean lifespan is 8,600 is really, really low, right? The odds of that happening are pretty low. So the chance of me just picking a really lousy sample probably didn't happen, right? These are probably different light bulbs. That this new light bulb does indeed last longer than the traditional light bulb. Everybody okay with that? So that would be a reasonable conclusion, right? That these two light bulbs are different and the new light bulb does indeed last longer. How much longer? We don't know that. We always can simply say is that they're different and the new light bulb appears to last longer. How much longer? Would not be able to tell from this analysis. It would not be 600 hours on average. This analysis does not support that. Everybody's okay? All right. So again, this is just a summary of what we just did. This was the original information. These were our hypotheses we made. This is the result on our calculator. What does this mean? So starting with the assumption the light bulbs had a mean life of 8,000 hours, close to 0% chance that we could have randomly picked a sample with a mean of 8,600. Therefore, we can safely say that our null hypothesis is rejected, that the two light bulbs were the same, that the mean for the new light bulbs should be 8,000. And we can accept the alternative hypothesis, that the mean is somehow greater than 8,000. Everybody's okay with that idea? Okay. All right. What if we have the same scenario, but this time the mean in our sample set was 8,200 hours. So let's do the same thing. We'll set up, or we'll record our information. So the null hypothesis, the population mean is 1,000. The sample mean is 8,200. The sample standard deviation is still 1,000. Our hypotheses are still the same, that the mean is really 1,000. And then, or the mean is actually more than 1,000, or 8,000, excuse me. So again, plugging in our calculator. So I did stat, over to tests, picked option 2, t-test, plugged in the values as shown here on the screen. So 8,000 for the null mean, or the population mean. 8,200 for the sample mean, 1,000 for the sample standard deviation, 25 for the sample size, and our alternative is greater than. So if I do the calculation now, my t-value is 1, and my p is 0.16 or 164. So that area that is greater than 8200 is this shaded region here in blue. So what we've done here, these last two examples, have been an upper tail test. That's this option here. When we select this, greater than option. When we try to figure out the probability that our sample's mean indicates the actual mean is higher than we expected. So we can still do, keep in mind, you can still do an upper tail test even if the sample mean is lower than the original mean, right? Because we're testing for the probability that the sample mean is bigger than the original mean. If our sample mean is lower than the population mean, we'd expect the probability that the sample mean is actually bigger to be quite low, right? But not zero. But not zero. Okay? So what if we wanted to know, okay, so our sample mean was 8,200, but what if we wanted to test if the new bulbs actually had a lower lifespan, mean lifespan than the original, than the population? So I do the same thing, but this time I'm setting up my alternative as less than 8,000. So again, I did stat, over to tests, picked option 2 for t-test, input 8,000 for the population, 8,200 for the sample, 1,000 for the sample, 25, and this time I picked the less than option. So it output for me, the t is still 1. Notice 8,200 is still 1 unit from the mean. But the p this time is, whoa, buddy, that's a big P, right? So the odds are quite good that the sample mean is actually less than 8,000, right? Like an 86% or 84% chance that the sample mean, the new light bulbs, average lifespan is less than 8,000, which shouldn't be very surprising, right? What was the standard deviation there? It was 1,000. That's a pretty big standard deviation. It's quite likely that even if we got a mean of 8,200, you picked, one absurd outlier and you could end up with something like this, even though everything else was averaging less than 8,000. You know what I mean? Only would take a couple of bad, like outlier-y light bulbs to do that. We call this version the lower tail test, since we're trying to figure out the probability that our sample mean indicates the actual mean is lower than what we think. Yes, I hope so.
I keep it a little graph. I probably did.
So I think it's probably this. Let's turn that off. So you did stat, tests, t-test.
And it untypes all the values. I type them in.
Yeah, fine, that's fine. We did that. Okay, so you want to draw?
Yeah. Okay, then how does, yeah, of course it's
Well, it's because I turned that plot off.
Oh.
Remember when I showed you in the y equals the plot one was highlighted?
Yeah.
That was why it was giving you the error, because you didn't have any data in L1 or L2 or something, and you're trying to graph the stuff that was in there. It's okay. All right. So we have this, right? And again, if you look at the picture, the lower tail, which way is shaded? Left, and what values are to the left? The lower values. If we looked at the previous picture for the upper tail, which way is it shaded? To the right. Where do the upper values live on the number line? To the right. Notice that there is still one other option down here, right? The not equal to option. Let's look at that. So again, let's say our sample mean was 8,200, but now we only want to know if the new mean is different from the old mean. So again, population 8,000, mean 8,000, sample mean 8,200, sample standard deviation 1,000. Our null is, the mean is 8,000, but the alternative is it's not 8,000. Or it's not 8,200, excuse me. So if I do that, I set it up the same way, except this time we pick the not equal to. So outcome is the t is still 1. The probability now is like 33%. And we have, it could be less than 8,200 or could be less than or greater than. So we have like two options. What do you think this one is called if we have two ends? Two-tailed, yeah. So this is the two-tail. You're trying to figure out the probability that our samples mean indicates the actual mean is different than we predicted. Again, from the picture, it's usually pretty obvious whether we're like upper tail, lower tail, or two-tailed. So far, so good? Okay. So the question now that we're left with is like, okay, we have these probabilities, but like, how good is good enough of a p-value for you to accept or reject a hypothesis, right? So let's look at the three or the four different situations that we had, right? So the first probability when the sample mean was 8,600, the p-value was less than 1%. Probably feels pretty good to on that one, right? The rejecting the null hypothesis there probably seems safe. And this one, the second one, where we thought that the mean was less than 8,000, that feels pretty safe at 84%. That's a big stinking probability. That feels pretty good, right? That the mean is actually less than 8,000, okay. But what about this one where it's 0.16, or this one where it's 0.32? Like, are those good enough? So to determine the value of p that will allow you to support or reject your null hypothesis, we use something called the level of significance. We abbreviate that number with the Greek letter alpha. So the level of significance, or alpha value, is the allowable percentage chance that a sample can be bad or unlucky or unrepresentative. Basically, even when we assume that our null hypothesis is correct, there's still a chance that we could have just picked an awful sample of data. You got really unlucky and got like a really unrepresentative sample. That could happen. So the level of significance is the allowed probability for that to happen. Like, how comfortable are you with being wrong on your hypothesis and just having the result of a lousy sample, right? So it depends a little bit about what it is you're doing. If you're doing like a medical treatment, you probably want a really low level of significance. You want something that's you feel really, really certain about, because the alternative is somebody probably gets hurt, right? If you're doing political polling, the level of significance could be much higher, because if you're wrong, it just means that the person you thought that was going to win the election might not win the election, which is not life or death, although you'd still want to not be wrong. But there you would be more comfortable with a higher threshold, more allowance that you just got an unlucky sample. The level of significance is arbitrarily set at the start of the experiment, but must be clearly identified before the calculations can be interpreted. The most common levels of significance are 1%, 5%, and 10%. Why do you suppose those ones? They're just round numbers, yeah. There's nothing magic about them. If you're doing something medical related, I would expect something more at the 1% level, right? If you're doing something, like money related, probably 5% is good enough. If you're doing something like predictive, maybe 10% is acceptable. Like the political analysis option, 10% might still be acceptable there. Everybody feel okay? So once with a level of significance set, we can use that to interpret our p-value. So the p-value, again, represents a probability, starting with the assumption that your null hypothesis is true. The p-value is the percent likelihood that you would be able to find another data set that is worse than your current sample. So could you get the probability you get a unlucky or less representative sample than the one you got? So what this means in a practical sense, when p is small, there's a very, very small chance you could find a worse or less representative sample than the one you currently have, making your sample an example of a very bad or very unrepresentative sample. And when p is very big, or close to 1 when I say big, and close to 0 when I say small, there's a very large chance that you could find a worse sample or less representative sample than the one you currently have, making your sample a relatively representative one, or a relatively good sample. Everybody's okay with that idea? So the p-value just tells you, okay, if we're randomly selecting this, how really representative is your sample to the population? Did you get something that is close, something you'd expect, or not so much? All right, with a given level of significance, you can decide whether your sample represents a likely or unlikely sample by remembering that large p-values are good. So if the probability, the p-value, is greater than or equal to the level of significance, this would indicate that our data set is better than the acceptable level of bad or unrepresentative, indicated by the level of significance. Therefore, our data supports the null hypothesis, or that we should accept the null hypothesis. Please note, by accepting the null hypothesis, by definition, we reject the alternative. Right? You can't accept both of them. If you pick one, it's automatically rejecting the other. Or if you support one, it's automatically, evidence against the other. If the p is less than alpha, this would indicate that our data was worse than the acceptable level of bad or unrepresentative, indicated by the level of significance. Therefore, our data contradicts the null hypothesis, so we should reject the null hypothesis And by definition of rejecting the null hypothesis, we accept the alternative. So in our first example, when our mean for our light bulb sample is 8,600, the P we got was very close to 0. That would reject the hypothesis that the mean is still 8,000 and would support the alternative hypothesis that the mean is bigger than 8,000. Everybody's okay with that? In that third example where we had a mean or a sample mean of 8,200 and our null hypothesis was that the sample or the actual mean was less than 8,000. Our P was 0.86. That's massive. That's going to be bigger than any level of significance you'd expect. So there we would accept the null hypothesis that the mean is of our sample is really less than 8,000. So again, in summary, if P is greater than or equal to alpha, we accept the null and reject the alternative. If the P is less than alpha, we reject the null and accept the alternative. Everybody cool? While it is fine to say you reject a hypothesis, it is technically incorrect to say you accept a hypothesis. This is simply because it's easier to show with one sample that a hypothesis is wrong. But you really need much more data than just one sampling to really confirm with 100% certainty that a hypothesis is true. So instead, we say, instead of accept, we say fail to reject. Okay? Would this be something the IB people are going to be picky about? Yes. So vocabulary is important, especially in statistics. Acceptance is a much higher standard than just failing to reject. So it means fails to reject is like, maybe that's still right. We haven't proven it's not right. Because again, one counterexample is really all you need to prove something is not right. To show it is correct, you need to show every time it's correct. And that's a much higher standard statistically to cross than just to like, it's wrong. Wrong is easy in math. Right is much more difficult. Okay. All right, since the p-value is typically not exactly 0% or 100%, there's still a chance you can make a mistake when making your final evaluation. So, we have the truth say that the null hypothesis is actually true, but our analysis said we rejected it. Or that the alternative hypothesis was actually true, but our analysis said that we should we should reject that one, right? So these are examples of errors. So when the null hypothesis is true and we don't reject it, that was the correct result. That's what we wanted to have happen. When the alternative is true and we reject the null hypothesis, that's the correct decision. That's what we want to have happen. Now, when the null hypothesis is true, but our test tells us to reject, that's called a type 1 error. And when our null hypothesis is not true, but our test says, well, it fails to reject it, that's called a type 2 error. Anybody think of a real-life example in our recent past where these type 1 and 2 errors came into play for every single American multiple times? I don't know, a year. What just happened like 3 years ago? COVID. Were the COVID tests 100% accurate? No. How many of us at one point tested positive but didn't really end up having COVID? That when you took a second test, you were negative right away, right? That happens. What is that? What type of error is that where we tested positive but we weren't really positive? So our test told us rejected, but it was actually true, and then our test was negative, or our test was positive, but it was not true. So if it was we tested positive when we shouldn't have, that's a type 2. The more concerning piece, though, from a epidemiological standpoint, would be the situation where you test negative, but you're actually positive, because then you go out and spread the virus some more. That's a type 1 error. So when you're devising a medical test, you want to really not have any type 1 error, the possibility of that being really, really low. But you'll accept some type 2 error being relatively high. It's okay for somebody to think they're sick when they're not, because they're just cautious. And you can always do another test to, confirm. So like in all the professional sports, they have drug testing, right? You guys are aware of this? I think it's probably, yeah. Typically when they do the drug testing, they're going to split your urine sample into 2 batches, like an A sample and a B sample, to reduce the possibility of a type 2 error of you testing positive when you really weren't using some, banned substance, because they're going to do the same analysis twice. So the odds of you testing positive when you shouldn't have been positive 2 times is massively lower than you just catching 1 type 2 error. To catch 2 type 2 errors in a row is very low. But that's one of the reasons they do stuff like that, is to, this is real life. People have this done, whether it's medical testing or other kind of testing. Oftentimes you do it twice to eliminate the possibility of one of these type 2 errors, particularly when you're testing positive for something. Okay. So let's look at another situation. So a comparison of the amount of nicotine that could be inhaled from cigarettes of the same brand differs between countries. Why would that be? Yeah, laws. Different countries are going to have different laws regulating the amount of nicotine you can legally put in a cigarette. That shouldn't be surprising, right? There is some suspicion that local cigarette companies boosted their cigarettes' nicotine content to maintain or increase present addictive levels. A study of 40 randomly chosen cigarettes was conducted to investigate this issue between 2 European countries. The recorded average level of nicotine content in cigarettes in both countries is given below. So in country A, we had 0.85 milligrams per cigarette with a standard deviation of 0.2 milligram per cigarette. In country B, the average was 1.3 milligrams per cigarette with a standard deviation of 0.18 milligram per cigarette. Does the nicotine content in the 2 countries differ? Now we're assuming that these cigarette companies are going to put the maximum amount of nicotine allowable in their cigarettes. Is that a fair assumption? I think probably for the most part, right? We don't have a high opinion of the cigarette companies. They want to get as many smokers as they can. We're going to use the 5% significance level to test this. So on just inspection, do they appear to be different?
Yeah.
Seems like it, right? The average is quite a bit different relative to each other. So this is a different kind of test, though, from what we've done, right? Because we're not comparing a known thing to a different thing. We have we have two samples, and we want to see, are these really come from the same pool or different pools, right? Are these two samples different? Everybody's okay with that? So this is called, the previous examples were one sample t-test. This is now going to be a two sample t-test. So to do this, again, we're just going to use the calculator. You're not expected to be able to do this calculation by hand. You're just going to be responsible for being able to use the calculator to do it and then be able to interpret the result. All right, first things first, we start by writing out our two hypotheses. So, hypotheses. The null is that they are really the same sample, that these are nicotine contents in these two countries are the same. So we just have, in one country, it seems like, the story about cigarettes' nicotine level being boosted illegally would seem to be supported by that number there, but let's see. So how would I represent that symbolically? That the means are equal, or that the difference of the two means is 0 for the populations? Everybody's okay with that? The alternative is that the nicotine content in the two countries is different. So the means are different, or that their difference should be not 0. So far, so good? Okay, calculator time. If you have your calculator out with you, I invite you to follow along. I'm going to start by pressing the Stats button, tabbing over to the Test tab. From the Test tab, we're going to pick the two sample t-test. That's option 4. In your screen, you're going to have something that looks like this. You're going to tab over to the Data option, or the Stats option, excuse me. And then you're going to input the stats for this problem. So the first sample mean is 0.85 with standard deviation of 0.2. We said in the problem there were 40 samples taken. The second sample mean is 1.3. Its standard deviation is 0.18. And again, there were 40 samples taken. And our hypothesis that we're going to be checking is that these two are different. Yes, that the sample mean, or the population means from these two populations are different. And this is no for pooled. What pooled means is that the two samples have equal variance. This is the only type of two sample t-test that will be on the IB exam. So let's change pooled to yes. You will not have a unpooled example on your exam. And then we're going to hit calculate. Everybody's okay? So far, so good? So this is our output. Let's talk about what this stuff means. So the p-value is close to 0, right? So the p-value is definitely less than 0.05. Remember, we were at a 5% level of significance. So we can reject the null hypothesis, which says that these two things had the same population mean. Everybody's okay with that? So the average nicotine content from the population in country A and country B is different. This means, yeah, okay, that the nicotine content in the two countries is different. Now, what would you say if you looked up the law and saw that, well, by law, they're supposed to be the same? What would we conclude then? Those cigarette companies are cheating, right? At least in one country, they're putting their thumb on the nicotine scale, trying to gin up some more smokers. Everybody's okay with that? So like if you're a regulator, this is the kind of work that you'd be doing, right? If you're checking, like there's regulation in like alcohol content of stuff, like has to match what you're posting. If you're a regulator, that's what you're doing. You're going to take some sampling and do this kind of analysis to make sure that, the beer that Anheuser-Busch is putting out doesn't have more alcohol in it than it's supposed to, right? Or if you're in the FDA, or not the FDA, the EPA, and you're checking for like pollution, like the allowable pollution that a factory or whatever is allowed to emit. This is the kind of, you're going to take some samples and make sure that, that they're not putting their thumb on the pollution scale there and emitting more than they're supposed to. Okay. Anyways, let's continue on. So we'll do another example here. Some investment funds can be purchased directly from banks, whereas others must be purchased through brokers who charge a fee for the service. There is suspicion that investors can do better by buying directly, i.e. cutting out the fee from their broker. Researchers randomly sampled the annual returns from funds purchased directly and those purchased through brokers. The data given here are the summaries of returns on investment after deducting all relevant fees. So basically we're trying to test whether you can do better investing by yourself or with the broker. Now you'd expect the broker to have some expertise and steer you, into better funds, but they're going to charge you for that service. We're looking at to see if at the end of the day, could you do better just by yourself, removing the fee but losing the expertise, right? So our buy directly, our mean return, that doesn't make any kind of sense. Why does it have two different with return? Oh, okay. So this is like with fees factored in, and this is like without the fees factored in then, right? That must be what this is or something. Oh, standard deviation. Yeah, okay. I'm dumb. I just didn't read the thing correctly. Yes, okay. So the average buying directly, the return is 6.63, and the standard deviation is 6.6 or 6.12. And for the brokers, the average return is 496 with a standard deviation of 658. We're going to test at the 5% significant level the suspicion that investors can do better by buying directly. So we start with our hypothesis that they are different, that we can do better by buying directly, i.e. that, so our null is that they're the same, right? Excuse me. And the alternative, the one that we're going to be looking at, is that we can do better with direct than with the broker. So let's go ahead and set this up. So if we do that, our sample one mean is 663 and standard deviation 612. Apparently the population size should be 50. And then our second sample's mean is 496. Standard deviation, 658. Again, sample size is 50. We are thinking that the first mean, the direct, is better than the brokers. So that's going to be that mean 1 is greater than mean 2. And then for all these IB 2 sample t-tests, we're going to be doing pooled. So when we do this, here's our result. What's the number we really care about, though? The P. So our P is 9.59%, which was bigger than the 5% that we had for level of significance. This means we failed to reject the null hypothesis, which was that they were the same. So it tells us that fails to reject the null, which says that the null is saying they are the same. So that tells us that buying directly or buying from the broker does not have a change in return in investment, that you're getting the same deal either way, right? So our p-value is bigger than our alpha. So we failed to reject the null, which said that they were the same. So if we had reversed the order of our data, that is changing our hypothesis, so the null is still, they're the same. But here, what if we said, well, what if the broker's mean should be less than direct? Right? That buying from the broker is worse than direct, rather than in the previous one, direct was better than broker. What do you think is going to happen? Let's run the analysis and check. So here, the X1 is now the broker data. So our first sample is the broker, and the second sample is direct. We do that. Notice that we get the same p-value. So what does that tell us? Still, we failed to reject the null, meaning that the two investment options are really the same.
The order you put it in matter?
Yes. Yeah, so because down here we are saying U1 is less than U2. So U1 had to be the broker because our alternative is that the broker is worse than direct. So yes, the order mattered. We had to switch which one was sample 1 and which one was sample 2. Does that feel okay?
Yeah.
Note that the level of significance makes a big difference here. If we had been at a 10% level of significance rather than a 5%, you'd have seen that P is less than alpha, and we would reject the null hypothesis. and say that, oh, direct is actually better than brokering, or brokering is worse than buying directly, depending on which analysis we are talking about, the first one or the second one. Is everybody okay with that? This is where type 1 and 2 errors might be observed, right? It's also important to make note of significant level prior to starting the question. If not indicated otherwise, a 5% level of significance is considered the standard. So if they don't tell you, you can assume 5%. But as your level of significance gets higher, the possibility for these type 1 and 2 errors go up, right? Does that make sense? I'm going to stop here for today, as we're at an example. I want to pass back these tests that you guys took last time. We have to help me remember we're on slide 33. Let's see if I can put that down here. All right, let's see. What else do I have here to pass back for you?